So we've seen before that it's useful to think about the complete graph on n vertices. But we've also been looking at colorability, and we've seen that bipartite graphs are particularly interesting. These are the two colorable graphs. So we can talk about the complete bipartite graph. This is a graph that's got m blue vertices, n green vertices, and every possible edge that doesn't create a monochromatic edge. So for example, we have K1, 3 for one blue edge and 3 green. One blue vertex and 3 green. And we have K4, 3, which has 4 blue vertices and 3 green vertices. So the complete bipartite graph has lots of edges. Obviously, it'll have fewer than the complete graph on 7 vertices here because we're not allowing any edges between the blue vertices or between the green vertices, only across. And again, these come up in situations where we're considering assigning maybe networks of printers to computers or applicants to jobs and so forth. So one thing we can ask ourselves, a simple question, is how many edges are there? Question, how many edges does KMN have? So this is a very natural question to ask. And then we can say, okay, well, for every one of the M blue edges, you have to connect to N green edges. So the answer is going to be N times M. So this gives us an upper bound on the number of edges for a bipartite graph. And it turns out that if we do a little bit of calculus, we can get a really nice way to state a theorem. So here's the theorem. Let G be a simple bipartite graph. I want it to be simple, so no multiple edges, no loops, on n vertices. Okay, now I haven't told you how n decomposes for a bipartite graph. This is an example of a bipartite graph on 7 vertices. Then G has at most n squared over 4 edges. And we can say a little more in the odd case, but it's basically this statement, it has at most n squared over 4 edges. So why would that be the case? How do we know to bound this? Well, it turns out it's a simple exercise in calculus. So we know that the most edges, so let's do the proof. Okay, we know that K sub, let's not reuse n, so let's say Km has K times M edges, which is the most possible, right? That's why we call it the complete graph, because it has as many as possible. So our goal is to maximize K times M subject to a constraint. And what's the constraint? Well, K plus M, the total number of vertices, has to be N. So this is just a simple optimization problem. So let's let F of M equal K times M. This is the function that we want to optimize for. So remember that we have N is fixed. And we really want F to be a function of one variable M, but we know that K depends on M and the fixed value N. So this is equal to N minus M times M. Okay, so if we want to find the maximum value of a function, what do? We take its derivative. So F prime of M, we're taking the derivative with respect to M, so that's just a number. So we're going to get here, the derivative of n minus m is minus 1 times m plus n minus m. I could have multiplied through, but I kind of prefer just to do it this way. And what do I get? That's just n minus 2m. Okay, so remember that the maximum of a function occurs at f prime of m equals 0, which implies that n equals 2m. In other words, m equals half, exactly half, which of course you could make sense, right? Having k13 over here, right, only gives me 3 edges. But if instead I tried to do k22, I just did a little sloppy drawing of it, I can see that k22 gives me more edges than k13. So evening out the top and the bottom is clearly the optimal thing to do. But the calculus tells us that as well. So if m equals this, then that implies that, of course, k is also going to be half of n. And so the number of edges is equal to m times k, which is n squared over 4. Now be careful, because if I'm talking about something like a graph, this isn't actually true unless n is even. We need to be a little more careful if n is odd. If n is odd, we have to go to the nearest integer. And that's exactly when we're going to have a disparity between k and m in terms of their parity. And then we're going to get a situation like this. So that's okay. It's just something to keep in mind that whenever you're working these problems where you're counting something like edges, if you're going to use calculus, just remember that calculus doesn't understand about us liking integers. So you might have to make some adjustments.